Hello and welcome to the Math 171 Pre-Calculus Algebra instructional lesson on functions, the initial section on functions in this course, section 1.3, third section of the first chapter. This is an introductory section, so we're going to be talking about exactly what is a function and what is not, and what are some of the characteristics of a function. Basic, pretty fundamental kinds of things, and simultaneously very important concepts. We will be, throughout this course, speaking of functions, which is, in one sense, it's a rather abstract type of concept, but it's one that I believe, as you practice with it and work with it, do the homework problems and move on through the course, it will become much clearer. You become more comfortable with it, per se, as you go along. I remember myself when I first learned the concept of a function, I wasn't too comfortable with it. So that's not unusual if this is your first exposure of this concept. But we're going to start right at the beginning, and let's go ahead and do that. First of all, if you just have any set of ordered pairs, considering the two variables x and y, and an ordered pair specifically then being a matched set, a corresponding set of an x value with its corresponding y value, and typically those are written as the x value, comma, then the y value, and surrounded in parentheses, and we call that an ordered pair. Anytime we have a set of ordered pairs of two variables, that set of ordered pairs is known as a relation. Very simply, it's just known as a relation. And there's no restrictions on that. Any set of ordered pairs works. You could have 1 or 2 or 112, or you can have an infinite number of ordered pairs, as you do, for instance, in the equation of a line or a parabola or all sorts of different situations, even a circle. For instance, in the equation of a line, there's actually an infinite number of ordered pairs, different x values correspondingly with their particular y value. Now, that's a relation. Any set of ordered pairs is a relation. But to be a function, it's much more restrictive. Specifically, to be a function, we have the two sets of values for the two variables, the entire set of values for variable x and the entire set of values for variable y. And specifically with a function, then there is some kind of limitation, a very strict limitation here, in that for every single value of x, there can be only one value of y. Let me say that again. For every value of x, there must be one and only one value of y that matches with that particular x value. So the function is, in a sense, it's like a rule, it's an operation, it's a mapping process that takes you from each and every single x value to its very specific and unique y value. And that is the function then. It's that set of ordered pairs which takes you from every single x value to one and only one y value. And these two sets, the set of x values and the set of y values, have names. And if you've studied this before, you've encountered these names. Otherwise, here it is for the first time. The set of x values, the set of, as we say, the input values for the function, is called the domain. And the set of y values, the set of output values of the function, as we say it, is called the range. Now, if you actually have a set of ordered pairs, which is a function, it does have a domain and it does have a range. There's no question about that. It does have one. Sometimes it's a little bit tricky to figure out exactly what the domain and range might be, and we're going to be looking at that. But it does have a domain, it does have a range. So when is a set of ordered pairs not a function? If you had, for instance, lots and lots of ordered pairs, and you had two ordered pairs, say, that both had the different y values, but they had the same x value. So for instance, if you had the two ordered pairs 2, 3, I'm going to try to get the pen facility operating here. Here we go. Writing on the screen now. If you had the ordered pairs 2, 3 and 2, 4, say, then regardless of all the other ordered pairs there might be in this relation here, these two specifically right here disqualify the relation from being a function, because the same x value is being mapped to two different y values, so it's not a function. If, for instance, in a certain speeding zone on the highway, there was, if for instance the speed limit was 55 and you were speeding anywhere from 1 to 9 miles an hour over the speed limit, there'd be some sort of statute saying, okay, the fine for going 1 to 9 miles over this statute is such and such an amount of money. And then whatever your speed is could be the x value, and the fine would be the y value. There's one specific fine depending on what your speed, it's how many miles per hour you're going over the speed limit. If you go 10 or more miles over the speed limit, the fine would generally increase. But if you came up in court, you're dealing with this speeding ticket, and you come up and say, yes, Your Honor, I was doing 5 miles over the limit, that's in the range, that's in the from 1 to 9 miles over the limit, so the fine should be this much. And he said, nah, I don't feel like that today, I'm going to make it be this much. Then that would be an example of where it's not a function. It's not a predictable amount. It's not a fixed, finite, definite, unique amount. It can be whatever anybody wants it to be, and all of a sudden your input values do not all translate to one unique predetermined output amount. Okay, just as an example. This little chart right here on the page here is showing the time of day versus the temperature. And at any unique place at a particular time, there is one and only one temperature. You can't have two different temperatures at the exact same place at the exact same time. So mapping from the time of day to the temperature would be a function. However, when you think about it, if you try to map backwards from the temperature to the time, it's probably not going to qualify for being a function. Say if you mapped the time of day for full 24-hour period from midnight one night to midnight the next night, and mapped all the different and recorded all the different temperatures, say at every hour. Well, by the end of that 24-hour period, the temperature would have presumably typically gone up from what it was at midnight to hit some kind of peak during the day and then drop back off again by the next midnight. So almost certainly during the two nighttime periods, the early morning and the late night periods, you probably have the same temperature at some hour for 2 different hours. It might be the same, for instance, at 2 o'clock in the morning as it is at 10 o'clock at night. So if you went from your temperature values, say the temperature was 50 degrees both at 2 in the morning and at 10 at night, and go backwards from the temperature to the time of day, you got a problem. Because for that one temperature of 50 degrees, it can go to 2 different times, 2 a.m. and 10 p.m., and then, okay, don't have a function. So most of the time, if you have a set of ordered pairs that represents a function, if you try to turn it around and work it backwards and test and see if it's still a function, very often it's not. We will see later in the last section of this chapter how there are special times where you can take a function and do it backwards, so to speak, It's called an inverse function. It does work, but that's special cases. So key points here are to understand the two sets of values, the set of x values as the input values known as the domain, the set of y values called the output values, and that's the range. And we'll go through these characteristics here at the bottom of this first page together. Each element of set A must be matched with an element of B. And this is indicating then clearly that set A is understood as the domain, set B is the range. So first of all, this first one is actually important also. Every single element in A has to be matched with an element of B. Not only can it not be matched with two or more elements, but it must be matched with one. In other words, if you have an x value that has no corresponding y value, then you got a problem. That's not even an ordered pair. You've got a problem. So every single x value has to have a y value. And statement 2, some elements of B may not be matched with any element of A. This is something I really don't plan to get into any further with you. This is a very high-level technical point. Generally speaking, for a practical matter, we consider all the y coordinates that are used in the set of ordered pairs for any function to be the range of that function. It can be said that the range is actually greater than that and you don't use all the y values, but we're not going to get into that. That will go no further, I can tell you that right now. So the set of x values used by the function is the domain, and with just a little bit of smoothing over here, the range is the set of y values used by the function. Point 3, two or more elements of A may be matched with the same element of B. So it is okay if you have two different x values, they can have the same y value. Think about a constant function like y equals 3. That's an infinitely long horizontal line. It's got a slope of 0. At every single point along that line, y equals 3, the y coordinate is 3, not just for 2 points, but for an infinite number of points. The y coordinate is 3, and it runs the entire gamut of x values from negative infinity to positive infinity, and that's perfectly fine as a function. So yes, two or more x values can have the same y value. The point that you cannot have is two or more y values coming from the same x value. That's what you cannot have. And that's this fourth point. An element of A, the domain set, cannot be matched with two different elements of B. It can only be matched with one element of B, and it must be matched, that's point number 1, with one element of B. So it must be matched with one and only one element of the range. Now this is something, a couple of other terms right here, independent variable, dependent variable. We speak of the x variable if we are understanding the variable y to be a function of x. That's a key point right here. If we're in the realm of understanding the variable y as being a function of x, then y is the output value, x is the input value, the set of y values is the range of the function, the set of x values is the domain of the function, and we can furthermore say that x then is known as the independent variable and y the dependent. So all variables are not created equal with functions. The x variable is fully independent, can take on any variables it can take on, any values it can take on, but the y values are fully dependent on what the x values are. So there is a difference here. X maps to y. Y does not map to x. And for instance, determining whether a particular situation represents y as a function of x. This first one, x squared plus y equals 1, in example 2, when you solve the equation for y, you get y equals 1 minus x squared. And so yes, for every single possible value of y, of x, all the way from negative infinity to positive infinity, you square it, subtract it from 1, yeah, you're going to get one single number. So yes, y is a function of x, for example, a. Let's look at b. Negative x plus y squared equals 1. Once again, we have to solve for y by itself, get y equals some expression, and then test that and see if it's a function. When you solve for y with this negative x plus y squared equals 1 equation, you get this situation right here where y squared now equals 1 plus x, and when you solve that for y by taking the square root of both sides of the equation, you see what you get. Y is equal either to the positive square root of 1 plus x or the negative square root of 1 plus x, two different numbers. For instance, if x was 8, 1 plus 8 would be 9, the square root of 9 is 3. So if x is 8, y could perfectly well be either positive 3 or negative 3. Therefore, this equation does not represent y as a function of x. Negative x plus y squared equals 1. It does not, because there are two different values of y for most all values of x. Interestingly, if you were to evaluate this from another viewpoint, if you were to ask, does this equation qualify for x being a function of y, it would. This one would, and part A would not, for the very same reason. If you solve equation A, x squared plus y equals 1 for x, you'd run into the same problem. You'd get x equals plus or minus some square root of some y expression. But anyway, the point is with example 2b that y is not a function of x. Now, we need to talk about symbols, symbolic notation of functions and such as this. Many of you have seen this before, but let's go over it right from the beginning. The expression f of x, as we call it, this right here that I'm circling, f parentheses x, that does not mean times. So often in math you have something in a parentheses, it means times. No, none whatsoever. It doesn't mean times at all. It's say you got a function whose name is f, and the output of that function, the y value of that function f, if you input the certain x value, the output is known as f of x. And you will so often see these written something like this right here. Whereas previously you would have seen, for instance, just the equation y equals 1 minus x squared. We will now be writing equations in the format of f of x equals 1 minus x squared. Again, that f parentheses x is pronounced, it is spoken as f of x. F of x, that's how we say it. If the function's name was g, we would say g of x. If the function's name was h, we would call it h of x. And this output amount, for instance, for this particular function, f of x equals 1 minus x squared, the 1 minus x squared, yes, is the y value for each particular x value. It represents the corresponding y value for every single x value. And so it is a fact that as long as y is a function of x and the function's name is f, it is a fact that f of x does equal y. Y does equal f of x. So we can, for instance, I'm going to change the color of this if I can here. Let's see if this is doing it. If we, yeah, that worked. If we have, for instance, y equals f of x, and then continue on with another equal statement like 1 minus x squared. That is a perfectly fine statement. For every single value of x, y, its corresponding y value for each ordered pair is simply equal to 1 minus the square of x. But it's also true the output of this function f, the output of the function f of x is equal to 1 minus the square of x. So to say y equals f of x is absolutely true as long as y is that particular function f of x. Okay. Now with this notation, it gives us the opportunity now to input specific amounts into that parentheses. For instance, how much is y if x equals 2? Well, we can now say y equals f of 2, and since we're specifically looking at x being 2, we would say y, which just the y by itself doesn't allow us to introduce the number 2, but with this new function notation it does. So y is going to be what we're going to call f of 2. What's the output of this function when x is specifically equal to 2? So let me try to write, there we go, minus 2 squared. All right. Well, 1 minus 2 squared is just 1 minus 4. So y is equal to negative 3 when x is 2, and it's also absolutely accurate to say f of 2 for this particular function f is equal to negative 3. And so you can put any number you wish in here for x that happens to be in the domain of the function. And here's some good news. For polynomial functions, whether it's constant functions or first degree functions just with x with no exponent, or second degree functions like 1 minus x squared where you have a quadratic, x being squared, excuse me, or any polynomial function of any degree, the good news is that the domain is infinite. It has no limitations. The domain for the x values is from negative infinity to positive infinity. Now, the y values may not be so unlimited. For instance, with this quadratic 1 minus x squared, if we were to graph that, we would see that the domain is unlimited, but the range is limited. In fact, let's pause here just a moment and look at this. Let me, there we go. Let's call up Desmos and graph this thing and look at it. And I'm going to have to get rid of these markings. There we go. Okay, so y equals 1 minus x squared. There's the graph of this. And so it goes up to y equals 1, and then plunges down forever in both directions, off to the left and to the right. And yes, there is no limitation as to how far to the left you can go or how far to the right you can go. The point is the x values are absolutely unlimited. So the set of x values, the domain for this set here, let me put this on here. The domain then for this particular function, the domain, it's not the easiest thing writing with this device. Okay, the domain, one way to say it is to say it is all real. Cursive's kind of hard. Okay, here we go. All real numbers. Boy, this takes a lot of time to write this out, but it's worth it. I'm making a point here. The domain is all real numbers if we simply express the domain using the English language. But oftentimes symbols, as you well know, can shortcut a presentation information. So we can say all real numbers, or we can use, as you're going to be using in your homework and on the tests and all, interval notation as we call it. So we're going to say the domain is also the interval of values from negative infinity, comma, all the way up to positive infinity, and close the parentheses. So that's another way to express the set of x values, the domain of this function 1 minus x squared. The domain is all real numbers, but it's also in interval notation, negative infinity, comma, infinity in rounded parentheses. Please remember, with intervals, you can have either the rounded parentheses on the left end and the right end indicating either that the set does not include those numbers, the left end number and the right end number, either it doesn't include those, or in the specific case of negative and positive infinity, those are not fixed. Obviously, they're not fixed finite numbers. It's only a concept of the unlimitedness of the numbers, and so we use a rounded parentheses always for the infinities, either positive or negative. And we use rounded parentheses when the number is not included. If the set, say, went from negative 2, comma, to 3, if negative 2 and 3 were not included in the set, then we would use rounded parentheses around the negative 2 and around the 3. If they are included, as it comes up to be with the range here, then instead of the rounded parentheses, you'll probably recall, you use the square brackets. So let's express the range of this function now together here. This function, the y values, is the range, the set of y values. I trust you can see by this graph that the y values literally extend downward forever. There is no limit to how far down these y values go to the left and to the right. Absolutely unbounded. They decrease forever. So that's going downwards. But going upwards, the y values have a limitation. They only go up to 1. In fact, I'm going to use Desmos and highlight the coordinates of that uppermost point of this parabola. You perhaps recall it's called the vertex of the parabola, the maximum point of the parabola, because it has the maximum y value for the entire parabola. Parabolas that open upwards also have a vertex, but it's known as the minimum point instead of the maximum point. So this maximum point, yes, the x-coordinate is 0, but that's not the main point. The maximum point has a y-coordinate of 1, and that is the absolute maximum y value in the range of this function, f of x equals 1 minus x squared. So the range, if I can write this out now, let's get back to the pen facility. It's going to take a minute, but we can do this. It's all real numbers We're going to probably write this out one time because it takes too long, but for one time it's worth it. All real numbers less than or equal to, because that maximum value 1 is included in the range set, less than or equal to all real numbers less than or equal to 1. Or we can now write an inequality, which is pretty efficient. If it's from negative infinity to positive infinity, you can't really say x is greater than this or x is less than that. It's just infinite. But now it does have a limitation, so we can say or y is less than or equal to 1, or third choice, use our interval notation, which you'll be doing a great deal of with WebAssign, or interval from, remember with intervals you always put the smallest number first and end with the larger number. It's coming up from the negative infinity at the bottom all the way up to the number 1, but it does include the number 1. The parabola perfectly well goes all the way up to the point 0, 1. That point is not excluded. That point is included on the parabola. So we now close the parentheses on the right for the number 1 end with a square bracket. So in interval notation, the domain of this function is negative infinity comma infinity in rounded parentheses, but the range is negative infinity with the rounded parentheses, as we always use a rounded parentheses with either one of the infinities, comma 1 square bracket, indicating to the reader that the range of this function includes that endpoint number, includes the number 1. Okay, let's go back now to the section in the text. I want to show you one more thing in this particular portion right here. Evaluating a function. You can evaluate things that sound a little bit strange, but let's look at this together. It doesn't always have to simply be the input amount, does not always have to just be a number. It can be another variable or some expression in a variable as the input amount. And so this is a new function here, g of x. The function's name is g, and g of x is the output of the function. So g of x now equals y. And g of x is equal to, specifically, negative x squared plus 4x plus 1. And then the example evaluates 3 different values for the input variable. For the part A is where x equals 2, part B, x equals t, and part C, x equals actually x plus 2. Perfectly fine. So if the input value variable x for this g function is 2, and then everywhere there's an x in the expression of the function, we replace it, we substitute in, we plug in a 2 for every single x. So what that means is you get this computation that g of 2 is equal to negative 2 being squared plus 4 times 2 plus the 1. And then you just crunch the numbers. Negative 4 plus 8 plus 1 is 5. So g of 2 equals 5. And that's actually the y coordinate for the g function if x equals 2. Now, what if t is the input amount? Well, again, g of t then is equal to the function expression with t plugged in everywhere there's an x in the original expression. So it becomes negative t squared plus 4 times t plus the 1. And again, crunch the numbers and letters out, so to speak, and you end up with negative t squared plus 4t plus 1, and that is actually the answer. That's as far as you can take it. Well, what if you wanted to put in x plus 2 in for x? We are actually going to be doing this in a section, a couple sections hence. I think it's section 5 in this chapter, where we will do, for instance, horizontal shifts to the left of a function, horizontal shifts to the right. Actually, if you plug in x plus 2 for x, that's going to create for this function a horizontal shift to the left for graphing the function, but we'll look at that here shortly, not in this lesson. But that's what's happening here. Plugging in x plus 2 for x, what do? How do we calculate it? By simply plugging in x plus 2 everywhere in the original expression there was the variable x. So that turns into this. G of x plus 2, as we read it, g of x plus 2 then equals negative the quantity x plus 2 squared. And remember, when you have a quantity like that in parentheses squared, you have to expand the parentheses and use what most of us called the FOIL method, first, outers, inners, last. So it becomes x plus 2 times x plus 2. Anything squared is times itself. X plus 2 times x plus 2 turns into x squared plus 4x plus 4, that entire quantity being subtracted because it still has the minus sign in front of it. Okay, but you get the negative quantity x plus 2 squared plus 4 times this new input amount x plus 2 plus the 1. And then you expand the x plus 2 squared, get x squared plus 4x plus 4, still in parentheses being subtracted. Then distribute this minus sign to all three terms in the parentheses, making it negative x squared minus 4x minus 4. Multiplying the 4 times the x plus 2, distributing the 4 makes it plus 4x plus 8. Of course, still the plus 1. And so finally we get expressions down here where we're ready to combine all our like terms and get our final expression. And combining all the like terms, interestingly, the negative 4x and the plus 4x cancel out. We only have one x squared term, negative x squared, and the minus 4 plus 8 plus 1 turns into plus 5. So g of x plus 2 for this g function turns into negative x squared plus 5. Nice little box here about the absolute value function that you will probably want to take a couple minutes and look at it. This is a graph of f of x equals the absolute value of x. And a quick pointer here, this function f of x equals the absolute value of x, you'll remember absolute value takes any number and makes it a positive. If it's already positive, it just stays what it is, but if it's or 0, just stays what it is. But if it's a negative number, it turns it into a positive number. So if we have the function f of x equals the absolute value of x, it graphs this perfect V with its vertex at the origin 0, 0. And what's interesting about this is the point they're making here, that this graph can be, this function can be expressed perfectly as what is known as a piecewise function. A piecewise function is a function, piecewise function. It's a function that has different function rules for different portions of its domain. In other words, depending on how much the x value is, you could have a different rule for finding the y value. And this actually does not violate the definition of a function, because remember, as long as every single x value has one and only one y value, you're okay. You got a function. So if you have different rules for finding the x value for different values of x, that in no way violates the function rule. So interestingly, the absolute value function can be written as a piecewise function if you make the piecewise function as so, that f of x equals the absolute value of x, and then break it into a piecewise function in two parts. It equals either f of x equals either x for x greater than 0 and x equal to 0, or f of x equals negative x if x is less than 0. And let's think about that. How can, it sounds like it's saying the absolute value is going to come out negative. No, it's actually saying the absolute value is going to come out positive. If x is less than 0, class, that means that the negative of x, you're taking the negative of a negative number. And we all know a negative of a negative gives us a positive. So although it looks funny, it's okay. So when x is less than 0, that means x is a negative number, and the negative of any negative number will give us a positive number. So like I said, it looks funny, but it's okay. You will be working with some piecewise functions as we move along in this course, and just understand that it simply means that for different values of x, y obeys a different rule. In this one, as long as x is positive or equal to 0, the y value is x. If x is a negative number, then the y value is the negative of that negative number. In other words, a positive number. And the domain of the absolute value function is from negative infinity to positive infinity. It takes on every single possible x value with no exclusions. But the range is limited. The range never goes negative. All the y values are positive or 0. So 0 is the minimum y value, and it is okay. You can have 0. The absolute value of 0 is 0. So the range starts at 0 and goes to positive infinity. And since it includes 0, notice the square bracket on the left of 0, and always with infinity, the rounded bracket with infinity. Has only one intercept. The x-intercept is the y-intercept, is the origin, 0, 0. Here's another example of a piecewise defined function. F of x is equal to either x squared plus 1 when x is less than 0, or x minus 1 if x is greater than or equal to 0. And when you graph that, class, you get this funny looking graph on down below here. This graph right here is actually the graph of that function. And if you're trying to find the domain and the range of that function, the function does exist at x equals 0. Specifically at x equals 0, the function is x minus 1, so the y value is 0 minus 1, it's negative 1. And that's the absolute minimum y value right down here. The absolute minimum y value is negative 1. And then as you move up, it takes on every y value forever and ever on up. You come up to here, and then once you get up to about this high, you can keep going up either to the right or you can keep going up to the left and evaluate the y values. Both of these, off to the upper left and off to the upper right, both of those are unbounded. They go up forever and ever. So the domain of this function then is all real numbers, negative infinity to positive infinity, but the range of this function only comes down to negative 1. So y is greater than or equal to negative 1 is one way to express the range. All real numbers greater than or equal to negative 1 is another way. Or in interval notation, it would be negative 1 with a square bracket to its left, comma, infinity with a rounded parentheses after. And to wrap up this section, I want to speak of some specifics about domain, and specifically domain, even range, but specifically domain, as they are implied simply by the equation given for the function. Most of the time when we are given a function to work with, it does not have an accompanying statement literally written out and say the domain of this function is such and so. No. Usually that's not given to us. And we do well to understand the limitations to the domain of a function simply by the given expression of the function itself. And the two most common situations, class, where the domain is going to be limited either slightly, like eliminating one or two numbers, or very major kind of way, like with a square root function where tremendous range of values of x is excluded. Now, first of all, let's take the situation of a rational function where you have f of x is equal to some expression divided by another expression. Usually both of them have x in it, but if the denominator expression specifically has x's in it, we will call that a rational function. And here's the point. As you well know, we cannot divide by 0. So if you have a rational function, which is the function then equals some expression divided by another expression in x, then this domain is, there's certain values of x that are excluded from being in the domain. That is any values of x which would make the domain equal to 0. And with the x squared minus 4 equals 0, you can, x squared minus 4 as the denominator, you can literally find the values of x that make the denominator be 0 by solving the equation given by whatever the denominator expression is, and then just force it to be equal to 0. So for instance, you can just write x squared minus 4 equals 0. X squared minus 4 is the denominator, and just force it equal to 0 and then solve that equation. And you can factor left and right, of course, or you can factor the left side of the equation just into 2 parentheses, x plus 2 times x minus 2. It's one way to solve this. Yes, you could also add 4 to both sides and take square root of both sides, x squared equals 4, and you'll get the same answer. Let me write this a little more clearly here, if possible. Yeah. And so, since we've factored x squared minus 4 into x plus 2 and x minus 2, I want to remind everybody of a very important fact in math. If two numbers are ever multiplied together and the answer of the multiplication problem is 0, in other words, if you multiply two quantities together and the product of those two quantities is 0, then here's the rule. Either one of those quantities may be equal to 0, or both of them might be equal to 0. It's called the zero product rule and many other names. But the point of this is that it's very helpful to us in solving for particular values of x in equations if the equation is set equal to 0 and you have two or more quantities multiplied together to give you that 0. And here we do. We have the quantity x plus 2 times the quantity x minus 2 equaling 0. So that means either x plus 2 equals 0 or x minus 2 equals 0. We have to do both of those. And for the expression x plus 2 equals 0, then that yields, for x plus 2 equals 0, that yields that. This implies you subtract 2 from both sides, and we get the result that x equals -2. Then for the second one, for x minus 2 equals 0, you add 2 to both sides of that, and you end up with, after this arrow here, we end up with x equals 2. So what does this mean? We're not solving the equation. That's not what we're doing. When I say x equals -2 and x equals 2, instead of solving the equation, we have just solved its denominator. The denominator set equal to 0, and we found those specific values of x that are excluded from the function. These are precisely the values of x that the function does not exist at, because these two values of x cause the denominator to be 0. Either 2 squared minus 4, or the negative number -2 itself squared. -2 times -2, negative times a negative, all gives you a positive, and 4 minus 4 is 0. So 1 divided by 0 is not difficult, it's impossible, it's undefined. So, bottom line, for a function like this, where you have some expression over another expression, you're dividing by some expression in x, the domain of that function is limited in that it will be all real numbers except those numbers that make the denominator be 0. So the domain of f of x equals 1 over x squared minus 4 is this. It's all real numbers except -2 and +2. So x takes on all real number values except -2 and +2. There's two numbers excluded from its domain. The text gives you this term implied domain. It's simply implied because it's not stated there, oh, by the way, -2 and 2 are not included in the domain. It doesn't say it, but we as people skilled in algebra understand that the domain of the function cannot include any x values that make the function expression be undefined. So we cannot divide by 0. So x being -2 and 2 are excluded. Similarly with square root functions. The very simple point is you cannot take the square root of a negative number and obtain a real number. Yes, you can get a complex number, but we're not going there. We're sticking with the xy coordinate plane, and for y to be a value on the coordinate plane, it has to be a real number. So the domain of any square root function is limited to those values of x which cause the contents of the radical, what you're taking the square root of, must be either 0 or positive, 0 or greater than 0. And so, for instance, if you had, let's look at an example, if you had f of x equals square root of 2x minus 6, and you were asked to tell the domain of this function. Well, it's not all real numbers. For instance, if we let x be negative, if we let x be -5, then 2 times -5 is -10, and -10 minus 6 more is -16. You'd have the square root of -16. And for those who remember your complex numbers, that would be 4i or even -4i. But we can't go to the i's. We've got to stay with real numbers. So x cannot be -5 because it makes the contents of the square root radical to be a negative number. So the smallest the contents of the radical can be is to go down to 0. So one way to do this is just simply write out the contents of the radical, whatever it is, in this case 2x minus 6, and force that to be equal to 0, create an equation making that equal to 0, and then solve for x. And when you solve for x, of course, you get that 2x plus 6, I'm sorry, yeah, well, if you add 6 to both sides, but you get, takes too long to write all this out. You simply get, adding 6 to both sides, we get, let me cross this out, you get just that 2x equals 6. And then dividing by 2 to get the specific value of x, you get x equals 3. So x equals 3 is the endpoint of the domain. Either x is greater than that or x is less than that, depending on the square root expression. In this case, it's going to be 3 is the smallest value of x that works, and any values of x greater than that work. If you had like 6 minus 2x inside the radical, 3 would be the largest value of x, and all values less than that would work. But for instance, x equals 3, then 2 times 3 is 6, 6 minus 6 is 0, you're taking the square root of 0. If x is 4, then 2 times 4 is 8, 8 minus 6, you're taking the square root of 2, no problem. Square root of a positive number, no problem. If you had x was 5, 2 times 5 is 10, 10 minus 6 is 4, square root of 4 is 2, so that's perfectly fine. You're taking the square root of a positive number. So the point is, the domain here is all values of x greater than or equal to 3. So it's, you could write it like this: x is greater than or equal to 3, or just do the standard interval notation. square brackets around 3 because it does include 3. 3 is perfectly fine for this function. That's the lowest value of x that works for the function. There is no highest value. It goes up forever without bound. So parentheses with the rounded parentheses after. The infinity symbol with a rounded parentheses. So the domain is 3 square bracket on the left, comma, infinity, rounded parentheses. And that is an introduction to functions, class. This was a explanation of the third section of chapter 1 of your text, section 1.3. And again, I hope this is helpful to you. Please let me know if you have any questions. We're going to wrap this up now, and I do wish each of you a good rest of the day.